Okay, I want to go through an example of how we go about solving a flash drum or designing a flash drum using the graphical method. So here's my example where we have methanol and water to be separated from each other. We have a given concentration of methanol in the feed. We have a flow rate of 100 mole per second, and we have a specification of the vapor to feed ratio of 0.5. So this is the information that we're given, and we want to find L, V, Y, X. So let me just box that. So this is what we're essentially the setup for this problem. And we're running this in a flash drum again. So first thing, of course, we always do, we draw ourselves a diagram so we can make sure we get all the details correct. Let me just do that. And got ourselves our feed fraction, and we're looking for V and Y, and L and X. And so there we have it. And we can quickly just do a material balance, or look at the material equations. V over F is equal to 0.5, and we can just go ahead based off of F and overall material balance, find that V is equal to 50 moles per second, L 50 moles per second. So there's our material balances. So now we just need to find Y and X, concentrations of the liquid and vapor streams. And what we'll do is we'll simply go ahead and create a McCabe-Thiele diagram for our flash drum and use that to go ahead and determine Y and X. So first thing we want to do when we do that, using the graphical method, is come up with an equation for our operating line. So in this case, let me just write out F is equal to V over F is equal to 0.5. So that was just given in the problem. And our operating line equation is equal to Y is equal to 1 minus F, this is little f, over F times X plus Z over F. So that's our equation. Okay, so if we go ahead and take little f, plug it into this equation, we just left with a simple operating line. Y is equal to negative x plus 1. So that is our operating line, and that's what we're going to use to go about solving this problem. So here's our vapor-liquid equilibrium data, our xy plot, and just to be complete here, I'm just going to write out y equals negative x plus 1. That is our operating line. So you remember that once we have this line, we can draw it and we can find out where it matches up with our xy vapor-liquid line, and that will tell us our x and our y. So z was given as 0.5. So we can use that as a starting point. We could just plot y equals negative x plus 1, but it's often easier just to start at the z value, which would be right there. So that's our z right here. Right there, y equals x equals z of 0.5, and then we just have to plot this with a slope of negative 1. So if I go ahead and plot that correctly, and again, if I was plotting this in a real method, I would be using a ruler, but since I'm just drawing this on my iPad, getting the lines, it's not perfectly straight, but it's good enough for this exercise. So the slope is negative 1, it crosses the y equals x line at 0.5, so that's our operating line right there in red. So then we just need to go ahead and find out right here where those two match up, and then we go ahead and take the value there, and that gives us our x and our y. So from where those two match up, I get x is equal to 0.29 and y is equal to 0.71. And those are my answers right there. So now I know the mole fractions coming out of our flash drum. Now, again, with this graphical method, I want to do as best I can using a straight edge, a ruler, when I'm actually drawing this out. but there is a certain amount of reading the tables, so you might get 0.30 for X or 0.28 or 0.31. So there is about a little bit of fudging when it comes to reading the chart. So you might get slightly different answer depending on how you draw your line. But that's okay, as long as you're close. Since it is a graphical method, it's not 100% exact, but it will give you more or less a good answer towards solving the flash drum. So that's the whole McCabe-Thiele method or graphical method for solving a flash drum. There you have it.